Okay, so we've had a chance to look at the energy levels for the harmonic oscillator, and we saw that it's evenly spaced energy levels. But what do the actual wave functions look like? And so, as you might expect, these wave functions are not simple sine waves. And so the wave functions are described, they're indexed by this quantum number v. They depend on our variable x. And the general formula that we have is that we have a normalization constant that depends on v, nv, hv of alpha to the 1/2 x e to the minus alpha x squared over 2. Now, what is alpha here and nv and hv? We'll look at that now. So alpha is a collection of constants, and alpha is equal to k times mu over h bar squared raised to the 1/2 power. So it's just a bunch of constants that are collected together to make it a little bit easier to write all this out. N indexed by the quantum number v is a normalization constant, and it's equal to 1 over 2 raised to the v times v factorial to the 1/2 power times alpha over pi to the 1/4. All right, and so this is, again, just a collection of constants as well. So then the hv alpha to the 1/2 x, this is what's known as the Hermite polynomials. Hermite being the guy in the 1800s who decided that this would be a fun equation to solve. And so these Hermite polynomials, I'll just list the first 4 of them. You can see table 5.2 to get a longer list from your textbook. But h, when v equals 0, we'll just use another variable here, squiggle or zeta. So the first one's really simple. It's just equal to 1. h1 is equal to 2 times whatever our variable is here. And remember, our variable is alpha to the 1/2 times x. h2 starts to get a little bit more complicated. 4 zeta squared minus 2. And then h3 is equal to 8 zeta cubed minus 12 zeta. And this is a whole series that just keeps going. Now, these don't intuitively look like, and then we also have this exponential that's at the end of it. That's there for every single function that we have. Now, it's not necessarily intuitive what these look like, and so I like to visualize them. And so I've got a figure from your textbook. This is a plot of what these wave functions actually look like. So going from v equals 0, v equals 1, v equals 2, v equals 3. So we notice that v equals 0, we get something that looks roughly like a Gaussian, centered about x equals 0, right, where the bond isn't stretched at all. So we get this shape up and down. And then v equals 1, we get, these are just a little bit like the harmonic, or like the particle in a box wave functions, but we also have these tails on the end. Right, the particle in a box doesn't have these tails. It just ends right at the walls of the box because of the way we define the problem. And so here we get down and up, down, up, right? So we get this. And then on the right-hand side, this is the square of the wave function. And so this shows you the probability distribution of the particle. And so according to the quantum harmonic oscillator, one interesting thing is that at the lowest energy level, we get, again, the exact opposite of classical behavior. Classical behavior, if we think of a pendulum swinging or a spring, a mass moving back and forth on a spring, it'll slow down at the turning points where it turns and goes the other way. And that's where we expect it to spend the most time. And so the probability should be highest near those turning points and a little bit lower towards the middle. We get the exact opposite behavior for the lowest energy level. The highest probability is right in the middle, where, sort of at its resting place. And as it's wiggling back and forth, the turning points actually have the lowest, right? The lowest probability. So this is, again, quantum is not the same as classical. And so that's, a theme, of course. And so if we want to use these formulas to write out some of these wave functions explicitly, so for example, psi 0, right, we use n0, h0, alpha to the 1/2 x, e to the minus alpha x squared. Let me move that so you can actually see it. And so we can plug in all those values, and we will get alpha over pi to the 1/4 times 1, e to the minus alpha x squared over 2. And I forgot the over 2 here. Right, and so this is, if we plot this, that's this function over here. And we can keep going with psi1, psi2, et cetera, et cetera.